Polar conversion. I'm going to replace u with r cosine theta and v with r sine theta. If I do that, theta is stuck between 0 and 2 pi, and r is stuck between 0 and 1 because this is a unit circle, right? Anywhere I see a u, I replace it with r cosine theta. Anywhere I see a v, I replace it with r sine theta. Let me go back to this integral. This integral here is actually 8 over root 3 integral 0 to 2 pi, 0 to 1. So I took the 2 that was here, and I pulled it out, and that's why that's an 8 now. And then I had u squared plus v squared, which is r squared, right? That was the whole beauty of the polar, is that if I were to take this and replace u with that and square it, and then this, square it, Pythagorean, it would become r squared, wouldn't it?
But then it would be r.
But then you need another r, right? Good. So you have r squared here from that. And then you have r because, well, you did a change of variables again. So you had another Jacobian that you didn't have to calculate. R is always given to you with polar. You don't have to compute the Jacobian for polar conversion. And then what? dr d theta. And I think that's pretty straightforward. I'll just leave it at that. Okay. I don't know, this feels pretty good. For me, in terms of my history of this section, I feel pretty good up here. Are y'all following this okay? As long as you don't ask me why the Jacobian. Okay. If I have some time at the end, if I get through this next example, I might talk about it. But then you'll leave here more confused than you were when you started.
Does that determinant setting up the scaling factor for transformations?
Is it what?
Setting up the scaling factor for all the transformations are not necessary.
Is the Jacobian determinant setting up the scaling factor?
Because if you're doing a transformation from one image to another, it's being scaled, right?
It is being scaled, yes. It is exactly doing that. It is establishing what you need to scale your little infinitesimal area by in your new image, like what it needs to be scaled by to maintain equality from one. You could almost say from one space into another. I mean, think about just a simple transformation. If I take this box, 1, 1, and I decide to do a transformation that takes that box over to 2, 2, right? Then an infinitesimal area here, right, is going to be scaled up also over here. And so I need to somehow account for that when I'm doing my integration. That's what the Jacobian determinant does. But I still haven't explained to you why those partials do that. That's the part that's hard to explain. All right, let's proceed. This last example, I don't give you the transformation. So we have to come up with it on our own. So we're going to do the double integral over d instead of rd of e raised to the x plus y over x minus y. And we're integrating this over this trapezoid that is given these vertices. So I'm going to go ahead and draw this. So 1, 0, 2, 0, 0, negative 2, and 0, -1. There we go. No transformation is provided. So for this transformation, it looks like we could do line segments, couldn't we? Little line segments like we did on the first example I did today, where I say, hey, where does this little line piece go? Where does that little line piece go? Where does that one go? Where does that one go? In fact, because it's a linear transformation, it's not. We haven't picked the transformation yet, have we? If it's a linear transformation, then we could just take those points over. But there's no transformation given. So I need to come up with that. What is the what is the x going to be? And what is the y going to be? What's the function, right? These are both functions of u and v. Now there's something very subtle here, but important. You know when you're doing an integral like this, back in Cal 2, if you were to do that, what technique would you use? Just what we call like a basic substitution. Not trig sub or anything like that. Basic substitution. So you would say, hey, look, I'm going to let u be and then something, right? That's what we're going to do here. We're going to let u be something and we're going to let v be something. Instead of trying to actually come up with x is something with u's and v's and y is some things with u's and v's, instead of approaching it this way, let's start by just, I don't know, let u be something and v be something and let these have x's and y's in them. This is kind of reverse. Instead of when you're given this stuff, it's great. We can work it out. But when you're not, you have to start by defining what you want u and v to be. So take a shot at it. What do you think? I mean, just look at the thing up there and just what would be a decent candidate? X plus y for you? Okay, I'm game with that. And what about v? X minus y. By the way, would you want to integrate this? No. Would you want to keep this in this space with x and y? I mean, maybe you could break that down as a type 1 or something, but would you want to integrate that with respect to x or y? I don't think you would. That would not be fun to integrate that with respect to x or y. In fact, I wonder what the computer will do with that. I'm not sure that we could. Let's see what it does. So I'm going to do a double integral here. I'm going to do exponential of x plus y over x minus y. I went back and did it. Oh, wow. It enjoyed that quite a bit. Exponential, this is an error function, I believe. I think it's safe to say it had some trouble. Yeah? It had some trouble. Now, if I gave it like the type 1 region here, if I gave it some limits of integration, I think it could handle it. But as far as just like a general antiderivative, it's not enjoying that at all. And nor would you enjoy that at all if you had to integrate that. Well, yeah, because you would have to integrate. You would have to first find the antiderivative of this with respect to x or y. You would need to do that at some point, and that the computer couldn't even do it. So maybe this change of variables is worth it. All right, so there's the substitution that we are going to try, right? There's no guarantee that this is going to work. We already fundamentally have a problem, though, and that's the way that we proceeded in the previous two examples is that we worked with x equals and y equals, didn't we? So we could take the partial with respect to x, partial of x with respect to u, partial of x with respect to y, and so on and so forth to get the Jacobian, right? And we also used those when we were substituting over here, like finding the equations of the lines and plugging in. So my first goal is to see if I can make these turn into x is some function of u and v, and y is some function of u and v. So can we turn those into these?
Yes.
Okay, how?
Solve for x.
Okay, you want me to, I heard solve for x here. I also heard solve for y somewhere. Let me solve for x on that one. Just go for it. If I do that, I get x is equal to u minus y. Okay, now what? Solve for y in the other one? Solve for y here. Y is equal to x minus v. Substitute, which means, I think what you mean is, you want me to replace that y with this? Or I could replace this x with that. Either way, right? All right, so let me do this one. I'm going to do this one. I'm going to rewrite it. X is equal to u minus y, but y is x minus v. So x minus v, like that. So that means x is equal to what? U minus x plus v. So move the x over. 2x is equal to u plus v. So x is equal to 1/2 u plus v. Bam. I now have x in terms of u and v. What about y? Now I can go back to this, right? I can go back to this one. If I go back to this one and plug in, I'm going to get y is equal to x, but what's x? 1/2 u plus v, but then minus v. So this is 1/2 u plus 1/2, take away 1, so minus 1/2 v. That's y. So here's what I've got. This right here, I didn't know what x and y was, right? I'm going to go ahead and say x is equal to 1/2 of u plus v, and then y is equal to 1/2 u minus v. So if you would have looked at these two, right? If you would have looked at this in the very beginning, I don't think that you would have said, look, I'm going to let x be half of u plus v, and let y be half of u minus v, right? You wouldn't have done that. But if you just kind of take a shot at this and say, look, I'd really like to separate these two things so that the x's and y's aren't mixed both in the numerator and denominator. Because that's what makes the integration hard, is that if I had to integrate this with respect to x, I've got x's both up and down. By making the substitution u and v here, this is going to become u and this is going to become v, right? Then your variables are separated, and when you integrate, that'll be an easier integration to do. All right, we've got it here. Now, are those linear transformations? Those are linear transformations, aren't they? That means they should take line segments to line segments. They should also take points to points, and then we can connect with line segments. So how would you like to do this? You want to label them and then plug them? If you label them, I think it pops right out. Watch. What is this? What is the equation of that line right there? Y is 0. What is the equation of that line right there? X is 0. Okay. And then the other two, we have to figure out those equations, don't we? I mean, if we're going to do it, may as well practice, right? This one is y is x minus 1. Slope of 1, y-intercept of -1. And then this one is x minus 2. Those weren't too bad, were they? Now I write these down, right? I take these and I write them down. So let's try, which one do you want to do first? Doesn't matter. You do the constants first. Let me do x is 0. If x is 0, then what does that equation become? 1/2 of u plus v equals 0, right? Isn't that what this means? If x is 0, this equation becomes that. Uh-oh. And then this is 1/2 u plus 1/2 v equals 0. U equals negative v, or v equals negative u, right? This is, I'm going to solve for v and make it v in terms of u. And the reason I'm doing that is because I'm going to choose to draw my axes like this, u and v. So like u is like the x usually is, and v is like the y usually is. So I'm solving for y, so to speak. So what does that look like over here? V is equal to negative y is the same as y is negative x. So this is a diagonal like this. Right? I'm not sure, is this a better region or not? Did we choose the right thing here? Let's see. What's the next one I should do over there? How about y is 0? If y is 0, then you're going to get, this is 0, right? And if that's 0, u must be equal to v. So you could solve that or no? I better write it down. This is saying 0 is 1/2 u minus v. And then get rid of the 1/2, multiply both sides by 2. You get u minus v is 0, so u equals v, or v equals u. This is like x equals y, isn't it? So this is the diagonal the other way. Let me label these. This was v equals negative u, and this one was v equals u. I'm hoping for some better results here. What's next? What should I?
X minus 2.
You want to do y equals x minus 1 or x minus 2? I heard x minus 2. We'll do that one. If I write down y equals x minus 2 up here, then I write down what y is, 1/2 u minus v equals x, which is 1/2 u plus v, but then minus 2. I'm going to clear fractions. I'm going to multiply everything by 2. U minus v equals u plus v minus 4, because that got hit by 2 also. U's cancel. V's don't. So v should be 2. So move this over. You get negative 2v equals negative 4, so v equals 2. All right, v is 2 is a constant. That's a good one, right? On my graph, that's v is 2. Horizontal line. One more. If I do y equals x minus 1, won't it be this same expression right here, except minus 1? Right? Then multiply both sides by 2. U's cancel again. Solve for v. You should get v is 1 this time. And that would be here. Well, I see the region. It's that one right in there, isn't it?
It kind of looks like it just turned it.
Yeah. So you might be arguing here that we have not achieved anything by doing this. But what we have achieved is the ability to integrate. Because you can't integrate this with respect to x or with respect to y. You're not going to be able to do it. So even though the region didn't really improve that much, we are now going to be able to do the integration. Now, I still need to transfer this over. This region right here, How would you want to deal with this region? Type 2 region. Type 2. Now we're using V's and U's, not X's and Y's. But here what we would say is that the V is stuck between two constants and the U's are between two functions of V, which means you have to go back and solve each of these for U, which is, you had that earlier, Eric, but I don't think you saw that coming yet at that point. But all right, so that's what we'll do. But before we forget, we need the Jacobian, right? We need the Jacobian in here. So the Jacobian all right, should be a constant, shouldn't it? Because it's a linear transformation. So we have the partial of x with respect to u, which is a half, times the partial of y with respect to v, which is negative 1/2, minus partial of x with respect to v, which is a half, times partial of y with respect to u, which is a half. And what you get here is negative.
Negative 1/2.
Yeah, we have these two together is negative 1/4, and then minus 1/4 again. So it's negative 1/2, but then absolute value. So negative. I'm sorry, 1/2. Did I say that? 1/2. Okay, so it's negative 1/2, but then absolute value is 1/2. That's a whole lot of halves being put together just to get a half, huh? All right. Time to convert. This right here becomes, I'm going for it here. I'm going for broke here. I'm going to see if you follow this. The Jacobian is going to come out because it's a constant. Remember with polar coordinates, the Jacobian is r. That can't come out, right? Because it's not a constant. All right. The only reason this Jacobian comes out is because it's a number. It's fixed.
Would you have to put your restrictions for?
That's what I'm about to do. I'm going to see. That's why I'm saying I was going to go for it. I'm going to try and give the restrictions and just have the completed integral up here. So I'm going to start with my bounds on v.
So it's
1 to 2. Okay, now my restrictions on u. So the bottom one, which is this one, solve for u. U is negative v, right? So this is going to go from u equals negative v up to u equals v. That's u equals v. So this is a type 2 region. I'm looking like this. Bottom function is really like the left one, and then the top function is like the right one. And then the integral e to the it's this over this, right? But remember, we said this was u and this was v, right? So this is u over v. U over v. No, you still have. Go back to our original substitution.
Yeah, no, I was just doing that.
Okay, I'm good. Continue. All right. So that the Jacobian already came out. D u d v. There it is. Now I'm just curious what the computer will do if I type that in instead. So if I do exponential of u over v respect to, what is it first? U, then v. That still had a little bit of trouble. Now if we put the bounds in, we're going to be fine. I'll put the bounds in. I didn't put the bounds on the other one, so I wanted it to be a fair fight. Okay, if I go bounds 1 to 2, and then negative v to v. I don't even know if y'all can see that, sorry. someone want to erase the board, or you don't want to keep that up there? Don't care. I forgot the Jacobian. It's 1/2 out there, right? D U D V. There we go. So you get a decent answer. You get a decent answer. I'd like to do the integration, at least the first part of it. If I were to be trying to integrate this right here with respect to u, what would it be? V e to the u over v. Because what you're really doing is you're looking at this right here as e to the 1 over v times u. And 1 over v is a constant. So what you have to do is you have to scale out by that. And when you scale by 1 over v, you're really scaling by v. So if you take the derivative, if derivative of this with respect to u should give you back this. So you see how we were able to do that? And then you plug in. Now you would evaluate this at u is v and u is negative v. So if you replace v here, you get what? 1. And then so you get v times e. If you plug in negative v, you get v times negative 1. So, v times negative, e to the negative 1. Did I say v times 1 or v times e? Doesn't matter. See, as soon as we start plugging things in, I just shut down. It's just like, would you all like me to work through this, or we got like 13 minutes left, or you want to work through it, or I don't care. I'll work through it. Okay. All right. So you've got to make sure you're clear on this first integration, though. That the antiderivative of this with respect to u is v e to the u over v. If you're not clear on that, please talk to me after class and we can see if we can't clear that up. U is negative v and u is v. And then we'll integrate that with respect to v when we're done. Now this is 1/2 integral 1 to 2. And now let's plug in. So if I plug in v here, I get v over v, which is 1. I'm not touching this. So v times e to the 1. So that's just ve, right? Or e times v. I'm going to put e times v because e is a number, v is a variable. So I always like to put the numbers in front of the variables. So that's what I get when I plug in u is v, minus now plug in negative v. So negative v over v is negative 1. So v times e to the negative 1. V times e to the negative 1. Right? That's what I get. And then dv. You can't factor, this e is in the denominator really, so. But I'm not too worried about integrating because this is a number, right? E to the negative 1 is a number. E is a number. I just have v and v, so I can integrate that with respect to v. So if I integrate this now with respect to v, I have 1/2. Here comes the integration. I'm going to do these term by term. What's the antiderivative of this with respect to v? 1/2 e v squared. And then minus antiderivative of this with respect to v is again 1/2. Let me put e to the negative 1 out front. V squared again like that. And I'm evaluating this 1 to 2. Dang it, I was hoping for 0 to 1. Almost there, almost there.
Can we just factor out the 1/2?
You can pull out a 1/2 tonight now. You want me to do that?
Yeah.
I'll pull out a 1/2 right now, and that'll make it a 1/4. Now I still have to plug some stuff in here. So the 1/2's gone. Okay, if I plug in 2 here for v, I get 4e minus 4e to the negative 1. 4e minus 4e to the negative 1, and then minus, now when I plug in 1, I get what? E minus e to the negative 1, like that. And those are like terms, aren't they? I can combine those. So I've got 1/4 out front, and then 4e, take away e, that's 3e, minus 3e to the negative 1. What did my computer say? How what? Yeah, the computer said the answer is 3 and then negative 1 plus e squared over 4e. Right? That's what it says.
Yeah, they factored out the 3/4, but they combined the denominators.
Yeah, so that's the computer's answer. So is ours right? 1/4, 3e minus 3 over e. That's what this means. If I get a common denominator between these two, I have to put an e here and then e on the top, right? Then that's 1/4, 3e squared minus 3 over e. And then pull the 3 out, and I've got e squared minus 1 over e, like that. Okay, I mean, we're there. Yes? They flipped the order, and I put the 4 back in there. I don't know why. Okay. That's it. Change of variables. What do y'all think?
Where's the homework?
Oh yeah, the homework. Yes.
On the final, would you give us a transformation?
Final's probably going to be like 10 of them. No. I don't know. If I did a transformation on the final, it would be a short and sweet one. Where most likely I'd give you the transformation. It'd be linear. Everything would move over real quick and easy. Yes.
You're always going to tell us when we have to use change of variables, and we're supposed to see it.
Okay, the question is, will I always tell you whether or not you need to use change of variables? Maybe not directly, but what I'll say is evaluate this integral using this substitution. Like, I'll give you x is equal to some function of u and v. If not, I will prompt you and say, use change of variables to do this. Yeah. Yes?
You got a few minutes? You want to talk about the Jacobian?
Do I want to?
It's your call, man. It's your call.
I actually don't. The problem is this. Here's what you need in order to do it. You need to know how to draw a surface with the vector function. So right now, when we draw surfaces, three-dimensional surfaces like a sphere, we use like x squared plus y squared plus z squared equals 9. If we want to draw a paraboloid, it's an equation with 3 variables, right? When we first started this class, one of the first things we did was we learned how to draw lines with vectors. Then we learned how to draw curves with vectors. We took derivatives and things like that. We need to know how to draw a surface with a vector function. Once we can draw a surface with a vector function, then what we do is we look at that region over here. Like if we're trying to transform, I can very loosely do this. You're free to go if you don't want to stay, that's okay. If you take this region and let's say we want to map it over to something that's going to be nice, what we do is we take a little infinitesimal patch of this, and that little infinitesimal patch could be all weird shaped like that. And what we do is we figure out how we draw this with vectors, and we take 2 vectors like this, and then we take the magnitude of the cross product of the vectors, which is the area of the parallelogram formed by the two vectors. And we can approximate this infinitesimal patch with that cross product. When you're looking at these these vectors, because they're on a curve that's drawn by a vector function, when you're trying to get tangent lines, basically, these are wind up being tangent vectors. Tangent vectors require partial derivatives because you're on a surface, so you have to like point in one direction, hold one variable constant, and go. And then turn the other direction 90 degrees, hold one variable constant, and go that way. So you start getting partial derivatives that represent these vectors. Then when you cross them, you wind up with a determinant. So that's basically it. But you have to understand that you can draw a surface with vectors first. That's about as loosely as I can explain it. We are going to do this, though. We're going to find the surface area of surfaces using vectors. It's just later. It's too early for us to start mentioning it here. All right, y'all have a great weekend, right? Weekend. I mean, I won't see you again until next week. Your take-home exam is due Monday.